And just like that, we have a machine learning model that can predict handwriting and recognize handwriting with over 99% accuracy after only one round of training. Welcome back, everybody, to another Python session. Today we're going to be working on building convolutional neural networks for handwriting recognition and object recognition. As always, before we start, I have a bunch of references available for you. The big ones today that we're adding are TensorFlow, which we've been working with for about a week. Reminder of your background information on neural networks. And then our projects today can come from many sources. The project we'll be working on today is specifically working on building a neural network that is capable of recognizing handwriting from images. This is a classic Python machine learning project, and so there are a ton of available resources. So I've given you just two that you can work off of if you need or if you want some more background. So to begin today, let's go ahead and do a quick review over neural networks. If you remember, in our last lecture, we talked about the difference between convolutional neural networks and recurrent neural networks. And one of the big differences, or probably the most important difference between them, is that RNNs, recurrent neural networks, have the ability to process temporal information. So RNNs are seeing data in sequences, and they're looking for patterns in those sequences. Whereas a convolutional neural network is a neural network architecture that is specifically using computer vision to recognize objects and patterns in images. So one of the defining traits of a convolutional neural network are the convolutional layers. And convolutional layers are unique because they basically are filters. So they convolve or adjust the size and parameters of the image by filtering them and transforming that data into weights that are represented as matrices to represent the data. And so these filters basically go through and create segments in images and then determine what value is found in each of the pixels of the segmented area of your image. So what this author is looking at right now is an example of the data we'll be working at today to recognize handwritten images. So in our data set, all of our images come in 28 by 28 pixel images, and this comes from the MNIST dataset. And this MNIST dataset is from the Modified National Institute of Standards and Technology. And this is basically a 800,000 image long data set that contains examples of handwriting from 0 through 9, so writing our numbers, as well as from A to Z, and over 800 examples of that. Now, specifically today, we'll be working with a subset of this dataset that contains 60,000 training images and 10,000 testing images. And as I said, all of these images come in 28 by 28 pixel format, and we'll talk some more about the specifics of this dataset here in a few minutes. Now, as I said, basically what these neural networks will be doing is taking the pixels of our image, converting them into specific weights and values based on the color or the RGB value of that pixel, and then convolving that or filtering it through a matrix, and then we will pull that information and then continue to process it through further downstream applications in our neural network. And so, for example, in this person's implementation of this neural network, they did a 3x3 matrix of pixels. In our instance, we'll be using 5x5 and then max pulling down to a 2x2. And that'll make sense here in a minute. So let's go ahead and get started. We're going to start with just a simple convolutional neural network. And as always, we've got to do some basic data pre-processing and cleaning. So the first thing that we'll do is go ahead and install some packages. Today we specifically need TensorFlow, Matplotlib, NumPy, and Pandas. NumPy and Pandas we in actuality will not be using. I just like to load them in because we are technically still doing a data science project, so it's good to have them around. As you can see, I already had all this downloaded, so our requirements are already satisfied. Next, what we'll go ahead and do is import some modules. So as I said, we're going to import NumPy and Pandas. NumPy is imported as NP, Pandas is imported as PD. Then we'll pull in Matplotlib, and specifically we're pulling in the PyPlot subpackage, and we'll import that in as PLT. We're going to import TensorFlow as TF, and then we have some specific subpackages that we need from TensorFlow, all within the Keras subpackage. So we're going to pull in the data set that we'll be using today, MNIST. We're also going to import the sequential structure for our neural network, which we've been working with for about a week or two now. Then we'll be pulling in some specific layers. Today we're going to use the dense dropout flatten conv 2D, which is the convolutional 2D, and then the max pooling 2D layer. And then the last one we need is a utility, and that utility is to convert a value to a categorical value. So rather than showing us zeros and ones, we'll convert it to a specific category within our data set. Okay, so we've got our modules pulled in. Now let's go ahead and load in our data set. Now the nice thing about using this pre-built data set is that we just have to load the data. We don't have to label it. We don't have to do any kind of other pre-processing. In theory, we're of course going to check to make sure that our data is being read in the appropriate way, but in theory we shouldn't have to do anything to this. So what we need to do here is pull in the MNIST dataset, and we can do that by just saying .load data, and we're going to set that equal to 4 new objects. So we're going to create the X-train, the Y-train, the X-test, and the Y-test. So the X-test and the Y-test are our validation parameters. The X-train and the Y-train are our training parameters. And to make sure that this data loads in correctly, we'll go ahead and print the shape of the X-train and the Y-train data. Okay, so let's go ahead and take a look at this. So as I said from our Wikipedia page, we have this MNIST dataset that contains 60,000 training images and 10,000 testing images. So in theory, our X-train and our Y-train should be 60,000 images long. And that is exactly what we get out. So X-train shows up as 60,000 images of shape 28 by 28. Y-train is one-dimensional, and it is 60,000 data points. The reason for that is the Y-train is the labeled data set that tells us what the X-train consists of. So the Y-train is the response to what X is, or the recognition of what X is. So the data is being read in the correct format. We have the correct number of images, and it looks like things are working so far. Just to double check that our system is actually processing the data set correctly, what we're going to do is plot 4 of our images just at random to make sure that they look correct and appropriate and they're what we want to work with. And so to do this, we're going to set up some subplots. So this first statement here says plot.subplot and then 2, 2, 1. This 2 right here is telling you the number of rows. This 2 right here is telling you the number of columns. And then this 1 right here is telling you where the subplot is located. So in quadrant 1. And so we've set up 4 of those. And then in the IM show plot, we have the X-train, and then we have the subset of the X-train, so the actual value or the position that we want to pull out of the X-train dataset and show. And then we're going to specify our color mappings. In this case, we're just going to do grayscale. And so we repeat that 4 times, and then we say plot.show. We'll go ahead and run that. And what we get out is this simple graphic here, but it's got our 4 plots here of X-trains index 0 through 3. And what we can see is this top one looks like the number 5. The one on the right here looks like a 0. The one on the bottom left looks like a 4. The one on the bottom right is probably a 1. And then you can also see that the graphs are showing the pixel values, or showing the image by pixel value. So we start up here in the top left at 0, and it works all the way down to the 28th pixel. And then same thing on the x-axis for all of our images, starting at 0 on the far left, working all the way to the right to the 28th pixel. So again, it looks like our data is being read incorrectly. This data looks fairly clean. It's also based on a predefined, pre-labeled data set. So I have a pretty good feeling about this at this point, and I say we are good. We can move along in our data checklist and actually get started for this experiment. Now, while the data appears to be read incorrectly, we still have to do some basic shaping and pre-processing for this data set. So for instance, in Keras, which is the subpackage we'll be using to train our convolutional neural network, it's expecting our images to be in a certain shape or format. And we've been dealing with this for 3 to 4 weeks now, so we've had to use the reshape function many times. The difference here with the convolutional neural networks is, while we will be using a 2-dimensional convolutional neural network to process our data, the input for Keras needs to have 4 different dimensions. So we need to tell the computer where its pixel readings are coming from, what the height and the width of the image is, and then how many channels there are. And the channels is a new dimension to us. But what channels basically means is, for this image that I'm recognizing at this time, how many output feature maps or how many filters should I apply to this image and then spit out. So we're telling it, for each image that it reads in from XTrain, please only provide me with one filter layer, or only create me one feature map of that image. Okay, and so when we actually start to read through the XTrain and the XTest here, basically what these are saying is create a new object called XTrain. So we're iterating over the previous XTrain object. And in this case, the XTrain object will be equal to xtrain.reshape. And what we want to reshape is the xtrain.shape at 0. So what this means is that we are wanting this to be our input array, and that we want it to go over the entire length of the xtrain array. And then we tell it the width and the height, which is 28 by 28. And then we tell it how many feature maps to create or how many channels to create, and just one. And in this case, we specifically want our data to be read as float 32 integers. And then we do the exact same thing for the testing data, because the XTest is a different set of images, but in the same format to be used as our validation data set. And so we'll go ahead and run that. And no output, which is a good thing. We're simply creating some, or instantiating some iteration variables here. Next thing we're going to do is normalize the X data. And to normalize our data set here, we are just going to normalize the values of the XTrain and the XTest data sets based off of their pixel values. So as we can see in this example plot up above, we clearly have black pixels and we have white pixels. So each of these pixels has a value in the RGB color values that is going to be somewhere between 0 and 255. 0 represents black, 255 represents white. So we could have any value within that range of values from 0 to 255. So to standardize our X values, we'll just simply divide the pixel values for all of the images across the entire data set by 255. So everything will be set on that scale. And then the next thing we have to do is encode our response variable. So our Y-train and our Y-test data set represent the labeled outputs of our data. So either 0 to 9, any of those numbers, or a letter from A to Z. And rather than having those as objects or floats or integers, however they're being read at this point in time, we want to make those categories, so that they are read as independent possible outputs from the model. So for instance, A is a category, B is a category, C is a category, and so on. So we don't want them to just be an object in space. We want them to be a set possible outcome. So to do that, we pull in the toCategorical function from Keras, and we are just going to reiterate over our Y-train and our Y-test objects, and we're going to say Y-train is equal to categorical of Y-train, and then Y-test is equal to categorical of Y-test. And then we're going to tell it how many possible classes there are in the entire data set by creating a new object called the number of classes, so how many possible responses, and that'll be equal to the Y-test shape at position 1. Okay, so just the total possible number of outcomes for this entire data set. So let's go ahead and run that. Looks like everything ran fine. We don't have any kind of output, which is good news as always when we're just creating variables or creating a model. Now we're on to step 2 of our pipeline. Step 2 of our pipeline is model selection. So as we've already discussed, today we're working with images and trying to recognize the writing found in an image. So this is a classic pattern recognition problem, and therefore, as we discussed in our Hacker Noon news here, when we need to recognize a pattern or we need to use computer vision, a convolutional neural network with some type of architecture similar to this is our best option. So this is the overall model that we'll be working on today. And this will be the large model that we're going to create. The first model that we're going to create will basically skip this second convolutional layer and the pooling layer here. So it'll go from convolution layer 1, pooling layer 1, to drop out flattened softmax output. And this guy has some fantastic figures. So we're going to go ahead and hop over here to his page so that we can talk through what a convolution operation actually does. So a convolution operation basically takes some image and creates a feature detector. And this feature detector is essentially just a matrix. So in his example, he's using a 3x3 matrix. In our example, we'll start with a 5x5 matrix. And this feature detector is just a kernel or a filter. So what happens is we create this kernel or this filter. And that filter is a specified matrix size. So in our case, it'll be 5x5. In this example, it's 3x3. And that matrix is laid over every possible position on the source image, and it finds the center of that image. It calculates the value of the pixel for all of the possible positions in that current kernel, and then the source pixel value is replaced by the weighted sum of itself and the nearby pixels. So for example, in this one, they have a source pixel matrix that has 0, 0, 0 in the top row, 0, 1, 1 in the second row, and 0, 1, 2 in the bottom row. And the output matrix for the kernel or the filter for the convolutional layer is giving us an output matrix of 4, 0, 0, 0, 0, 0, and 0, 0, negative 4. Okay, so that filtering is then taken and converted into a new pixel value for the next layer of our neural network. And so this 4 and negative 4 gets turned into negative 8. And how that's basically working is by taking the multiplication of the matrices and the values throughout the matrices and creating a feature map of the convolved feature, which is basically just the summation or the summarization of the original image in a new layer, so that we can reduce the size of the image and also create multiple feature maps for multiple detectors if needed. Now, after we have this initial convolutional layer, what we're going to do in our architecture is add a pooling layer. And the pooling layer will use a max pooling function. And so this pooling layer takes the original convolutional layer, where we've taken the image from 28 by 28 down to 5 by 5. And then in the pooling layer, we'll reduce the convolutional layer from a 5 by 5 matrix down to a 2 by 2 matrix. And then from the 2 by 2 matrix, we take it into the dropout phase and the flatten phase, and then a softmax probability function, and then through our output. So this is the general architecture that we'll be working with. And this is and these are the general concepts of how a convolutional neural network work overall. And just so that everyone is familiar with what flattening and dropout do, the flatten statement or the flatten layer basically takes the feature map after our max pooling stages and then takes it from a matrix shape into a one-dimensional array for processing. And then the dropout layer, essentially what a dropout layer does is you specify the percent of the points in your neural network to get rid of immediately. So, and this is done completely randomly during training. So in the example here on the left, this would be the fully connected neural network of a convolutional neural network. And after going through dropout, we can see over here on the right, this is what it looks like. So we determine how many of the points are going to be removed. For example, in our case, we'll be using 0.2 or 20% of the possible connections will be removed. And at that point, those are no longer activated. And so it forces the input to have less possible ways to work through the network. And hopefully by doing that, that random selection, you can ensure that you are not, one, overfitting your data, but two, that you also are getting the correct responses and reducing any possible redundancy in your neural network. Okay, so that's the basics of our model that we'll be using today. If you need more information, go ahead and click on this link right here. It takes you to the Kaggle page we were just looking at. So what we're going to do now is start building our baseline model. Our baseline model is going to be simpler than our large model, as I just said. So we'll refer back to this architecture as we work through this. So what's going to happen here in the baseline model is we are going to instantiate or turn on a model, and that model is just going to be equal to the sequential process within the TensorFlow package. And sequential just allows us to add layers step by step. So what we're going to tell the model to do after we've turned it on is we're going to tell the model to add a convolution 2D layer, and that convolution 2D layer is going to have 32 possible inputs of matrices that are 5 by 5 in size, and we're going to tell it the input shape of the image it's getting is a 28 by 28 pixel count with one channel as we specified above, and then it's going to use the activation function relu. And I skipped over the relu function the other day. We can quickly talk about the specifics of relu. Relu is a activation function basically to break down the linearity. So it's to reduce the linearity of the output of your model. So it increases the non-linearity of the weights and values because images are non-linear, not linear objects. So we use the relu activation function to increase the non-linearity of our data, which should help us better optimize and better fit our model. So that's stage one. That's this convolution layer. So after we bring an image in, it goes through this first convolution two-dimensional layer right here. After our convolutional layer, what we're going to do is add a max pooling layer. And so we're going to tell it model, so the sequential model we started earlier, add a layer, and we're going to say that we want you to add a max pooling 2D layer with a pool size of 2 by 2. So what this pool size means is I want you to take the feature map that was created in the convolutional 2D layer, which was a 5 by 5 pixel matrix, so in this layer right here, and I want you to downsize that to a 2 by 2 matrix for the pooling layer. So it goes through the max pooling function, and then you get an output of a 2 by 2 feature map for every possible section of the image. Now, after we add the max pooling layer in our architecture, we're going to go ahead and move on to the dropout layer. So after this first max pooling layer in our baseline model, we're going to skip these other two layers and go straight to dropout, and we're going to tell it to add a dropout layer where we're going to remove 0.2 of our possible connections. After we remove those possible connections, we're going to add a flatten layer. As I said, the flatten layer is going to take it from a matrix shape to an array shape or vector shape, and maintain the weights of that matrix in that new vector. After we add the flatten layer, the data is going to move through a dense layer, and that dense layer has 128 possible inputs. And again, we're using the relu activation function, which should increase the nonlinearity of our data. After that first dense layer, we're going to add a second dense layer. So we're all the way over here on the far right side of our neural network now. And in that second dense layer, it is going to have the same number of possible inputs as the number of classes in the data set. So the number of classes, again, was defined as the number of possible outcomes from the y-test data set. So every possible outcome in the y-test data set is in the number of classes. So those could be numbers 0 through 9 or digits 0 through 9, as well as letters A through Z. So we're going to add a dense layer that has that many possible categories or outputs, and then it's going to have an activation function of softmax, and softmax is a probabilistic function that determines if the probability of that weight occurring at that point in time or during that event. So that is the way that we're going to match our possible outcomes to our actual outcomes and try to predict the probability of that. Once we have added that second dense layer, then we're ready to compile our function. In this case, we'll be using model.compile, and we're going to use the loss function of categorical cross entropy. And so this categorical cross entropy basically compares the predicted output from the model to the true output of the test data set, and then optimizes the weights based on the atom stochastic gradient, which I showed you the other day, which is just this loss gradient over time. And then the metric that we're using to confirm the accuracy of our model here is just going to be an accuracy measurement, so a percentage of the accuracy of the overall test. And then we're going to ask it to return the model. So we'll go ahead and run this and build our baseline model. Now we're ready for step 4 of our pipeline. We're going to go ahead and turn on our convolutional neural network. So the first thing we're going to do here is call in TensorFlow Curious to clear the backend, so to remove any possible models that we may have just sitting in our workspace. And then the next thing we're going to do is turn on the model. So we're going to reiterate over the model variable, which was created up above in the baseline model. And we're going to say now in our space that the model object is equal to the baseline model, which is our defined function up above. Go ahead and run that. Shouldn't take any time at all. All we've done at this point is turn the model on. Now we're ready for stage 5, or step 5 in our pipeline, which is to train the model. So to train the model, we're going to say model.fit, and then we're going to tell it where its X training data is, where its Y training data is, which is our labeled output data set. We're going to give it its validation data, which is X test and Y test. We're going to tell it how many generations to train for, or how many epochs, which is equal to 10. How many images it can have in each batch size. In this case, just set it to 200. You can make it 400 or 1,000 or whatever you want. And then the verboseness. Now, the verboseness of our model we did not talk about in the last case. Verbose we had set to false. In this instance, we're going to turn verbose on. Verbose is basically just referring to the output from running this line. So if verbose is set to false or 0, you get no output. If verbose is set to 1, you get a progress bar for how the training is going. If verbose is set to 2, it tells you loss metrics, accuracy metrics, it gives you the progress bar. So verbose set to 2 is where you're going to get the most information while the model is training. Another thing that we're doing differently today that we did not do in our last session, in the last session we predefined the batch size, the evaluation steps, and the epochs above. So instead of having it inside of the models, we basically had iteration variables up above where we would just say like epochs is equal to 10. And then you could just call on epochs within the model if you wanted to keep it consistent across the board. It works either way. So we will go ahead and start fitting the model right now. It really shouldn't take too long. While this is a large data set, it's not too large, and our notebook here is set up to run on GPUs. GPUs are graphics processing units, which are specialized for working with images and processing pixel values. And you can see just within the time of explaining that we're already done, so it took 14 seconds. Let's look at some of our data here. So in the first round of training, our accuracy was 92%, second round went up to 97, third 98, fourth 98, fifth 98, sixth we get 99%. And you can see that our validation accuracy started at 97, then 98, 98, 98, 98, 98, 98, and we don't hit 99% until the 9th generation. But still, within 10 generations, we have a model, a simple baseline model that is capable of getting an accuracy metric about 99%. So after one round, that's really not that bad. Now, granted, these are small images and also fairly simple images. We're not trying to pick out a car versus a stop sign or do any kind of complex object recognition at this point. But it's still interesting to see how quickly this model works and the level of accuracy we're getting. So to confirm the accuracy of this model and the numbers we're getting from our fitting of the model, we're going to go ahead and actually evaluate the accuracy of the overall model. So we're going to create a new object that's called scores, and scores will be equal to the model that we just created above and fit above. And then we're going to call in the evaluate function, which is built into TensorFlow. And then we're going to tell it what is it evaluating that model based off of. So it'll be evaluating the model based off of the X test variable, which is the image data set that we've been holding to the side to test on, or to confirm or validate our data on, and then the Y test data set. And in this case, we don't need an output, so verbose will be set to 0. And then we're going to just ask it to print it for us. So we're going to say print the CNN, or convolution neural network error, and that'll be based off of 100 minus the scores times 100, so just calculating the percentage here. So we'll go ahead and run that. And we can see that after one round of training in a simple baseline model with only one network or one layer of convolution and pooling, we are getting an error rate of 0.99%. So less than 1% error after only one round of training. So that's actually pretty good. And now what we're going to do is take that initial model and we're going to add to it. So now we're going to take and build the architecture that we actually see in this image. So we're going to start with our input image. We're going to create a convolution layer. We're going to pull it down using our max pooling function. We're going to create a second convolution layer this time. create a second pooling layer this time, then it'll go through dropout, then it'll be flattened, then go through our softmax and give us an output. So this time, instead of just having one layer of convolution and pooling, we're going to add a second layer of convolution and pooling before we do our dropout and check our accuracy and compute our probabilities. So to do that, we first have to start by building a large model. So in this case, we're just going to define it as the larger model. And that larger model will be equal to model equal to sequential. So the sequential model again for TensorFlow to allow us to stack the layers of our neural network. Then we're going to call on model and we're going to say to add a convolution layer. In this case, we're going to allow for 30 filters, and those filters will be 5 by 5. You can leave this as 32 if you'd like. Totally up to you. Our input shape is going to stay the same, so it's going to get an image of 28 pixel width, 28 pixel height, and channels equal to 1. So we want it to send it through one filter or create one feature map. Then we're going to give it the activation function of ReLU again. Step 2, or the second layer of our architecture here, is going to be that max pooling function, where we're going to convert the 5 by 5 feature map that comes out of the first convolution layer into a 2 by 2 feature map in the pooling layer. Then we're going to add a third layer, which will be another convolutional two-dimensional layer. In this case, it's going to take that 2 by 2 and it'll have 15 possible filters. It's going to create a output matrix of 3 by 3 in size, and again have the ReLU activation layer. After that convolution layer, we add the second max pooling layer, and that again will take it from the 3 by 3 feature map down to the 2 by 2 feature map. After we get through the second layer of pooling is when we connect to the rest of the network. So the first thing we'll do is add in our dropout. Our dropout will leave at 0.2. Then we're going to flatten our matrices or feature maps down into our vectors. After we flatten them down, we're going to run them through our dense layer of our network. And that has 128 possible inputs, and it'll use the ReLU activation function. Then we're going to add a second layer of our dense network, which will have 50 possible inputs. So from the 128, it's going to take it down to 50, again with the ReLU activation function. And then our last dense layer is the number of classes to categorize these possible inputs down into the possible actual outcomes. And it's going to figure that out by using the softmax activation function, which again is our probabilistic function to calculate the probability of events occurring based off the weight of that event. And then lastly, we have our compile function. So we're going to take our model after we've added all those layers and compile it using our loss function of categorical cross entropy again, our optimizer being Atom, which is our stochastic gradient model, and then we're going to have accuracy as our overall metric, and then we'll just return the model at the end. So we'll go ahead and run that. Took no time. That function is now created, and we have the larger model that we can call on. Next thing we'll do in this new pipeline is instantiate the convolutional neural network. So we'll start by clearing our session again to get rid of the model from up above, and then we'll create the new model, which will be equal to our larger model. So let's go ahead and run that. Ran just fine. We're not expecting any outputs, so it seems like everything's okay. Now what we're going to do is actually move into step 5, and we're going to refit the model based off of these new parameters in this new architecture. So again, we just call on the model and we say fit this model based off of this X training data set and this labeled Y training data set. And then we're going to tell it where its validation data is, X test and Y test, how many epochs to train for, and the batch size. And in this case, we will not specify the verboseness of this function, which should result in a verbose of 2 for our output. So it should give us all of the possible metrics. And we'll go ahead and run this. Shouldn't take too long again. And there we go. So our larger model only took 22 seconds to run. Let's see how much faster or slower. The small model took 14 seconds to run. So we added 3 extra layers to our model in the large model and only took 8 more seconds. So really not too bad as far as the training process goes. Again, reminder, we're only doing 10 generations here, not like 100 or 1,000. So it will take longer as you add more. But let's look at some of our metrics here, see what we got. So starting right at the beginning here, we're only getting an accuracy of about 88%. By generation 2, we're already up to 96. Generation 3, 97. 4, 98. 5, 98. It looks like it takes till generation 10 till we hit 99% accuracy. But when we look at our validation accuracy, we can see that in generation 1, we had a validation accuracy of 97%, generation 2, 98, By generation 6, we're at 99. We drop down a little bit in generation 7, increase again in 8, increase in 9, and then 10 stays about the same. So I guess really 8 through 10 stayed about the same. But overall, it doesn't look like this model did too bad. So in order to check the accuracy of our model, let's go ahead and run step 6 of our pipeline here, which is evaluating the accuracy. And again, to evaluate the accuracy, we're just going to use the evaluate function, and we're going to reiterate over that scores object, and we're going to feed it the x test and the y test information. Again, we don't really need an output, so we'll set verbose to 0 or false, and then we're going to ask it to print the error rate of this model. Let's go ahead and run that. And you can see that our large model gives us an error rate of 0.74% after one round of training. So what that's telling us is that we have a 99% accuracy of our fitting of our model after one round of training. That's really not that bad, especially because the one round of training only used 10 generations of training time. So really this model does well overall. And when we compare that to our small model, you can see that adding that extra layer after one round of training drops our error rate from 0.99 to 0.74. So we cut out about 0.20% of our error rate by adding in those extra convolution, pooling, and dense layers to our problem. So that's what I had for you guys today. What we were really hoping to get out of this lesson today is the fact that while neural networks and convolutional neural networks seem complex, they are super prevalent in the environment around us. And working with convolutional neural networks in Python is actually rather simple. As you can see here, we did not need that much code, and we were really accurate in our prediction of the objects that were found in our images. Now, of course, there's other challenges to this. We were using very, very simple input images, whereas the real world is obviously going to be more complex and require more training and pre-processing of the images because of the pixel density that you will likely find in other images. But that'll honestly probably be the end of what we cover for neural networks this semester. In our next session, what we're going to do is start building our developer portfolios and setting up our GitHub Pages account so that we can get all of this work that you guys are learning and all of this material you guys are learning onto a public page to help you possibly land a job as a Python developer or just a general web developer or software engineer, whatever your goal is. So that's all I had for you guys today. I hope you have a great day. I hope you have an even better week, and I'll see you next time.